one side. I'm ready to use a logarithm. Log to what base? Base E, right? You could use some other base, but I mean, why? Right? Base E is the natural log. There's a button for that. Okay. So I'm going to say RT is the natural log 2. That's an equivalent equation. It's a one-to-one function, the natural log. Or I can just say by definition of the natural log. RT is the exponent which when applied to base E gives me 2. So it's the natural log of 2. And then T, the doubling time, is equal to natural log 2 divided by R. So, so why is a real estate agent interested in this? Well, the value of housing is growing at a steady rate R. How long will it take the value of your house to double? And how does that compare with the rate of inflation? Is that better or worse, right? That's, I guess, another consideration, but never mind that. You say that this is approximately 0.693 over R, and I'm saying that a real estate agent would call that 70% in the numerator, right? Because they're not interested in that much accuracy. 69.3% is the same as 70% for practical approximation. And so the doubling time for the value of your house, if the housing values are increasing at a rate R, will be computable by this formula. Actually, just if housing values are increasing at a rate of 10% per year, compounded yearly, then it'll take 7 years, roughly, to double the value of your property. Yeah, so this business of compounding, like here, or here, is notable since Albert Einstein, I believe, has a quote that's relevant here. He said, the most powerful force in the universe is the force of compound interest. The most powerful, that's like big. The most powerful force in the universe. And of course, Wall Street bankers know about this too. That's how they get filthy rich, by loaning you money at some rate. And they just make up the money out of thin air, so it doesn't cost them anything. But you get to pay for it. Because you're poor, you're probably honest, and you will pay for it.
I have a question on that topic.
Yeah.
So considering just in general, the E approaches, I think it's 2718, right? So that's the first year. If you do like the infinite amount of $1 on 100% interest, it's not relevant to this particular question, but E in general.
Yeah,
so
in general,
yeah, that's $1 at 100% interest if you were to calculate it an infinite amount of times at the end of the year. Is that a correct way to phrase that?
If you were to compound it an infinite number of times
Yeah.
per year, then it would be worth $2.72,
Right.
approximately,
Right.
at the end of the year.
Now, does that have to do with why credit cards are due every 30 days? Because it approaches 2.6, I think, at that point, and then waiting 2 months is like pointless.
That's a complicated question. Why do credit cards allow you to slide for a month?
How many times do they compound their interest in like a real life scenario? Do they do it once every day for 30 days?
I don't know. That's an interesting question.
Well, it wouldn't surprise me if they used Euler's number. I mean, at that particular point, because that would give them the most money in 30 days.
Yeah, I guess that'd be something to investigate if you're interested.
But that's one way I can imagine it, though, right? If I did $1 at 100% interest for a year, that would be like Euler's.
Compounded continuously, yeah.
Yeah. Okay.
And we have this model where at the end of 1 year, so you'd have R as 1 because it's 100% interest, T is 1 because it's 1 year, so you take your initial amount and multiply it by 2.7 and change. Okay, so that's the doubling time, and okay. So how about half-life? substance has a half-life of, say, k years. Then what can we say? Then we can say the amount there is, let's say A for amount instead of P for population. I mean, you could think of it as a population of molecules, I suppose, but it's going to be the initial amount, which would be A sub 0, times 1/2 to the T over K. So it's the same kind of thing, isn't it? Except instead of the multiplier being 2 for a doubling every k years, the multiplier is 1/2. We're cutting it in half every k years, right? All right. So that A of k, or A of 0 is going to be A naught, right? A of k is going to be A naught times 1/2 to the k over k, which is A naught over 2, right? And so there's your half. After what you started after k years. And so on, right? I could put it at 2k and I'd have 1/4. Right? Notice that you can also write this as A naught equals, or times 2 to the negative t over k. Why is that? Yeah, negative exponent means reciprocal, right? So I can take out the -1 part of that exponent factor of -1 and apply it to the base 2 and get 1/2.
On the third one right there, it's supposed to be k over k or t over k?
Well, the input is t in general. T goes there
Oh, yeah.
in the exponent, right? So if it's 0, then that's 0. So I just get 1/2 to the 0 is 1. But if it's k, then I didn't have to write the k over k. I could just written 1. I inserted inside. I'm plugging in t equals k, so my exponent becomes 1, and my multiplier becomes 1/2, and I've got 1/2 of what I started. So this is all in the realm of section 4.5, I think, exponential and natural growth.
It's 4.5.